Breaking news. Apparently, there's a bunch of strange crop circles appearing. It's a bunch of circles inside of circles inside of circles. And we're trying to figure out, is this aliens? John, can you get on the case on this one?
I don't know if it's aliens, like, per se, right? I don't know. It's kind of weird here, though. It's just, I feel kind of 2D. It feels kind of really complex. But some people are saying it's like a giant dartboard, you know? It's like, there's a circle and a smaller circle, and you hit the bullseye or whatever. And then they're trying to find a probability or something. I don't know what's going on here. I have a premonition that we're going to be working with complex numbers for a bit. So let me just tell you a little bit about them. Okay, so complex numbers, they're made of two different parts. A real part, where we call A, and the imaginary part, where we call B. You can tell it's an imaginary part because it's B times I. That's what we're going to define a complex number as. The absolute value, or the norm of the complex number, is just its distance from the origin. But that doesn't make any sense. It's imaginary. It's not a real line. Well, it's on a complex plane. You didn't see that coming, did you? And because it's distance from the origin, right, you can just take the square root of A squared plus B squared to find the actual distance.
Problem 1. Let z be a complex number such that the norm of z is less than 1. What is the probability that the norm of z is less than 1/2? Well, it turns out that because the norm of z, as we defined earlier, is actually just the absolute value of z, or its distance from 0, we can see that every complex number that's a distance of 1 away from 0 just lies on the unit circle, and every complex number that is within 1, a distance of 1 from the origin, is within that circle. And so this is our area. That represents every single complex number that can satisfy these conditions. And so we can do the same thing for the norm of z is less than 1/2. It's the same thing. It's a circle, but the radius is now 1/2. And so if you take the ratio of their areas, we can actually get the probability that these conditions are satisfied. It's like a giant dartboard. You just throw a dart and you see if you land on the middle one as opposed to the big one. Okay, cool. So if you do the calculations as you see now, it's just just look at that and it ends up being 1/4. Yeah. Problem 2. Let z be a complex number such that the norm of z is less than 2. What is the probability that the norm of z squared is greater than 2, or the norm of z to the 1/2 is greater than 1? What's up with the z squared and z to 1/2? I don't know, it's kind of icky, but there's a way we can actually deal with that. And there's actually a property that makes it super trivial. And the property is that the norm of z to the n is actually just the norm of z to the n. Here's how you prove that the norm of z squared is actually just the norm of z squared, and the norm of z to 1/2 is just the norm of z to the 1/2. Now that we know this knowledge, we can see that the norm of z is greater than 1 squared, or the norm of z is greater than root 2. And since it's an or statement, and the norm of z is greater than 1 includes the norm of z being greater than root 2, we can just focus on the norm of z being greater than 1. Once again, we can take the areas, right? But this time we're not taking the area inside the smaller circle, we're taking the area outside the smaller circle, but inside the bigger circle, and dividing it by the bigger area of the bigger circle to find the probability, which is just this. And we get our answer being 3/4. Problem 3. Let z and w be complex numbers whose real and imaginary parts are both selected with replacement from the set 0, 1, and 2. With the probability that the norm of z plus the norm of w is greater than the norm of z plus w. So what we can do is we can expand z and w in terms of a, b, c, and d, where z is equal to a plus bi, and w is equal to c plus di. And what we can do is we can expand it and plug in our definition for norm, then we can simplify it. Okay, so what's important is that we get to this part. AD over BC plus BC over AD is greater than 2. If we plug in x is equal to AD over BC as a replacement, or a substitution, we get that x plus 1 over x is greater than 2. Now, there's an interesting fact. The arithmetic mean will always be greater than or equal to the geometric mean. And there's a really neat way we can prove this for two integers. If you draw the circle, right, with like a or b splitting the diameter, the height from the circle to the point where a and b are split, actually, by properties of right triangles, is root a times b, which means that that's the geometric mean. And the radius is just a plus b over 2, which is the arithmetic mean. As you can see here, it's really intuitive that the geometric mean will never be greater than the arithmetic mean. And so we can plug that in, and looking at x plus 1 over x is greater than or equal to 2, and what we wanted to show was x plus 1 over x is greater than 2. The only case where it would fail is when x plus 1 over x is equal to 2. And plugging this into this quadratic, we see that x is equal to 1, which means AD over BC equals 1, which means AD has to equal BC. That's when it fails. And so we can check how many ways it fails, because if A or D or B or C is equal to 0, then both sides equal 0 and it fails. So let's say A is 0, then D could be 1 or 2. If A is 1 or 2, D could be 0. Otherwise, A or D could both be 0. That's 5 cases. And since there are two sides, you have 25 total possible combinations with 0. Then you have the possibility that they both multiply to 1. There's only one possibility, 1 times 1 is equal to 1 for both sides. And you have the possibility that they multiply to 2, which is 1 times 2. And since you can order them twice on both sides, that's just 2 squared over 4 ways. And you have the possibility they can multiply to 4, which is 2, 2, 2, 2. And so if you add all these up, you get 25 plus 1 plus 4 plus 1 to get a total of 31 ways that don't work. Subtracting that from the 81 ways that do work, we get 50 ways that work over the total number of ways that work, which is 81, to get our answer 50 over 81. Oh, and by the way, you know that 81 is the total number of ways that work because you have 3 possible choices and you have 4 inputs that it can go into, so it's 3 to the 4th, which is 81.
Oh man, well, it's too bad the aliens don't exist, but giant dartboard crops representative of math in the complex plane are pretty cool. You gotta admit that. And by the way, how's the weather over there?
I don't know, man. I guess it's kind of circly out here. Oh wait, what's that?
Thanks for reporting, John.
Call the police!